So process log and prevent race conditions. So which may be used for
Sorry, madam. So I got delayed.
no problem, sir. It's okay. Just I have started. Okay, so synchronization is very much important for preventing the race conditions. Already we have seen deadlock and and so the situation is if more than one operations are executed at the same time, so which are not scheduled in a proper way or proper sequence, and so not exited in the critical section correctly. And in those times, so you need some sort of synchronization. So already we have seen in somewhere some synchronization mechanisms. So for dot product and all, so we have to calculate and what we are doing is we are multiplying pairwise multiplication. So that time I told if some thread is not completed their pairwise multiplication, so that time if the thread 0 is going to access that particular location, so it won't get the data. Okay, so we have seen some sort of diagram and all. Okay, that is the situation. So we don't get the correct answer. Okay, some sort of errors or some hanging. So everything happens. Okay, for that we need some synchronization. Okay, so see here. Initially, we are setting either flag, maybe either true or false. Okay, so the first thread what it executes while not flag, S will be executed. After that, flag is set as false. So here, while flag S2 is executed and flag is set as true. And so here, what we have to consider is, so we are performing the atomic operations. Okay, and and the flag has to be volatile. So otherwise, some hanging will be happen. So next we'll see what is mutual exclusion. So if there are through two threads are there, okay, trying to access the same memory location, what you have to do is first try to what it will do is it will lock that memory location and try to access once it's wrote in the something onto the memory location, then it will be released. After that, the second thread will be accessing that memory location. Okay, so if both the threads are using the same memory location, so you have to perform lock and unlock methods. Okay, and okay, so in mutual exclusion, so what we can do is you can prevent some multiple threads accessing the same shared memory location at the same time. So already I told if it is a read operation, it is not at all a problem. So if both are trying to write at the same time, any one thread can able to write, other couldn't able to write. Okay, and okay, so here one example is there. So the thread IDs are either 0 and 1. Okay, there are two threads. One is 0, one is another one is 1. Okay, so here we are using the atomic. Okay, so while using the atomic, what happens is the process read, process, write. All the three operation happens at the same time. Okay, after that only that memory location will be accessed by another thread. Okay, so here there is one variable me, so that is id is assigned to that variable. So others will be having 1 minus me, flag of me equal to true. So flag of other. Okay. So all the operation completed, then it is released. Okay. So initially what happens? If one thread is accessing that memory location, it perform the lock, then do all the operations and then unlocked. So then that flag is assigned as fault. Okay. So if you want to guarantee the mutual exclusion, the variable should be assigned as a volatile. Okay. Otherwise, it may lead to deadlock. Okay. So volatile memory is an important concept. Just 1 minute. Okay, so if you are performing some synchronization mechanisms and you have to use the volatile variable, so the main reason is the variable which is declared as a volatile won't come into the mutual exclusion. Okay, so actually using that condition only we are performing the mutual exclusion. Okay, so otherwise what happened is it is also synchronized, it may lead to some other problem. Okay, so here volatile is given for the variable victim. So during the log, okay, so and some value is assigned and me is assigned to victim, that is id value is assigned. So id is equal to me, some statements are executed, after that it is unlocked, after that victim is assigned to me. So here also um, so it may leads to some lack of progress in the execution, and all the threads repeatedly takes the what it is called locks. Okay. So another one important mechanisms here in mutual exclusion is so Peterson lock. It is already, you people may know that what is Peterson lock and all. And here mutual exclusion is guaranteed and does not lead to deadlock. You know what is the deadlock? Okay, so both the process or threads trying to access the same memory location, that time deadlock may occur. And so to prevent the deadlock, you may have some critical session concept and all. So if anything is any process is accessing that goes into the critical session completed and come out of the critical session. Okay, so here there is one additional variable flag is used. The flag indicates and the thread is interested. Okay, so for accessing the memory location. Okay, so what that other variable says is you can do it before me. Then once that is executed, if any thread is interested to access that memory location, so that will be given chance to access, and after that the other is trying to access. One it is come out of lock, the other is trying to unlock. So here up to this we are having only two threads. So using, if you are having only two threads, what we can do is either you can perform lock unlock concept and So use some volatile and flag variables. So you can correctly maintain which thread can able to access, which thread is having the permission to access that particular memory location. Okay, so if you want, in while considering GPU and all, we are having n number of threads. We are not having only two threads or three threads or four or five threads. Okay, so we are having n number of threads. So we need some algorithm which is very much useful for using n number of threads. Okay, so in this particular algorithm, bakery algorithm, what happens is it will work with n threads, and also it is using first come first serve for increasing number of threads. Okay, and here also what happens is we are using the lock unlock mechanism. We should have some flag of array of flags, and we need also some additional variables. Okay, so with these variables only we can able to perform the um, mutual exclusion or synchronization. So in GPU, and so if there is no catches, okay, so the mutual exclusion works well. If you're having catches, it won't works better. Okay. So in GPU, already I told you are having warps. So once you are executing means all the 32 threads are combined together, and that means all the 32 threads are simultaneously executing the same instruction. Okay. And all the threads getting the same label with some priorities. Okay. And GPU, initially GPUs, there won't have any logs concept and all, because of the spinning cost in large scale. Okay, so the cost will be very high while using logs in GPUs. Okay, so but if you have used logs, it is very much useful for synchronizing the task available in the GPU, or synchronizing threads in GPU. Okay, so you can perform logs, or you can implement logs with the help of atomics or atomic functions. Okay, so already we have seen the atomics. There is some little bit concept of atomics here. I won't go into the all the function and all. So here the atomic means is it is a primitive operation, and so the effects of the atomics is visible fully. Okay, either it won't be visible, otherwise fully. It is never partially done. Okay, so it also needs some hardware support. Okay, other functions are atomic compare and swap, atomic min, atomic add, atomic sub. Okay, so many functions we have seen, and it will be working with both global and shared memory. You can use it for both. Okay, so already I told you while using the atomic operations, so what happens is you will read, perform some operation, and write on the same location. Okay, all the three operations. See here, one example is given in this particular example. So the value of x of 0 is incremented. Okay, so what happens is while performing this instruction, so first the register value will be loaded into x0, and the value is incremented, and after that, that is again stored to, that is first x naught value is stored to R1, and R1 is incremented. Then again back R1 will be stored to x naught. Okay, these three operations has to be performed while doing plus plus x of 0. Okay. So here, if you have used two blocks, one threads, that means in each block you are using a thread. Okay, first block you are using one, and second block you are using one at the same time. Then what happens is the same instruction is executed in both the threads. Okay. See here, and x0 is loaded to R1 and increment Rn and store the um, x0 value onto R1. Okay. So again, the next thread also using the same thing, load x0 into R1, increment R2, sorry, R2, and store again R2 back to x0. Okay. So in both the cases, the final value uh, which could be stored on either R1 or R2. That is R1 on R2, both are register. That could be 1. Okay, because x0 is having the value 0. So we are just incrementing the x0 value. Okay. Okay, so here while using the atomic INC, so here you can use atomic INC. So while using the atomic INC, what happens is, so atomic INC of x of 0. So it will ensure the x0 will be incremented by exactly by 1. Okay, so with the help of k1 and k2, and so irrespective of the execution order. See here, so in this particular slide, these two statements are executed initially. Okay, at first. So at the same time, here the 3 instructions executed. So after that only the x0 is stored to R1. Okay. So even though the execution order may change there in the thread, okay, so it won't be affect the result which is stored onto x of 0. Okay, that particular variable that won't be changed while using the atomic function or atomic INC, because here in this function we are performing the increment operation. Okay, so in the shortest path problem also, so instead of calculating all these things, you can use atomic min. Okay, so automatically the min value will be stored in the same memory location. Okay, so next is barrier. So here, what is barrier is, it is a program point where all the threads need to reach before any thread can proceed. So if you have set some barrier, what happens is, um, all the threads have been synchronized, and up to that point, so once it is all the threads come to that point, then only it allows to do the process or thread to some other uh, execution or process, whatever maybe it is. Okay, and so here the kernel is the implicit barrier for all the GPU threads. It's a global barrier because we are writing kernel program as a global function, and so we are having some function like, okay, before CUDA 9 it is somewhat difficult for synchronization and other things. So now all the synchronization is very much effectively used there in the GPU because of the latest CUDA APIs. And here we are having some function like grid.sync. Okay, using that you can use. And the thread and all, you can synchronize with the help of __ sync threads. Okay, so already we have used sync threads so many times. And so here, uh, um, so for data synchronization mechanisms also, not only for control, so data synchronization mechanism and all, so you can use the sync threads. Okay, and also it is very much useful for memory fence. Memory fence is nothing but if any threads is writing something on the memory location, that is visible to the other threads in the same group. Okay. And So it also execute the fence for all the block threads. Okay. So in a single block, all the threads can be seen whatever things are returned by some other threads in the same block. Okay. So using sync threads, you can obtain all that too. And so there are thread fence block and thread fence. Okay, these instructions are there for fencing the block and fencing the threads and everything. You can use those statements too. So reductions. Already we have seen the reductions too, and for dot product and all. So here in the reductions too, so we can use instead of synchronization, we can use atomic add, atomic min. Okay, so all these functions. So here one example is there, and there are some n numbers. Okay, so when barrier is set here, okay, what happens is, so these two numbers are added and stored, and these two numbers are added, these two are added, and these two are added. Okay, after that, these two is added, these two is added. At last, all the digits, last two numbers have been added. Okay, see here, and in this particular example, if we have used okay, so here one main important thing is, so you need sum of n by 2, 1, 2, 3, 4. Okay, n by 2 threads for adding these two numbers. Okay, so initially we are having n numbers means, so we'll need n by 2 numbers, and 4 plus 5 is added, and 3 plus 7, and 9 plus 3, uh, and 3 plus 2. Okay, so there are 8 numbers have been there. So we have considering, we are dividing into 2, and the first one, this first half first one and second half first one is added. Second half first half second one, second half second one is added. Likewise, it goes on. After that, only and after the next step also, what happens is an n plus 12 is added and 10 plus 5 is added. So now we are having only two values. Okay. So at last, all the values have been there in the first memory location. This is another one way. So here all the values are there in the middle. Here all the values are in the first thread, thread 0. Okay. So this will help for reduction. Okay. So both the diagrams in a single slide. That's all. And one more concept is there, the prefix sum. Okay, so here each and every thread pushes different number of work items. So this can be done with the help of atomics or prefix sum. Okay, see here what happens is 4 plus 3, 7 plus 9, 16 plus 3. So likewise it goes on. Okay, so either the output may be like this. The initial value is written as same, and all the other values are, the first one is added with the second one, and the result came second one is added with third one, and the result came third one is added to. Likewise, at last you will got the output in the last location. If you are start with 0, what happens is 4 is again displayed, and after that it comes before n minus 1. Okay. So you can apply the prefix sum in many different ways. Okay. And so for computing cumulative sum and histogramming, area under the curve, and binary index tree. So okay, all those areas you can apply the prefix sum. We will see some of the programs using this. Already I have pasted all the programs. First, we will see. Okay. In CUDA, you can write programs using C++ too. So all the things are same. The only difference is instead of std.io, you use IO stream. Okay, for input and output and all. Okay, so I have taken the same program here in this particular program. So two arrays have been added. Okay, two arrays have been added the same way in the C, and so allocated memory, and the arrays are initialized and the kernel is launched. Okay, okay. Uh, so the what the CUDA device synchronize will do. So it waits for the CPU will wait for GPU to complete. Okay. So then after that you can check the errors. Okay. So if there is any errors you can check. Okay, using Fmax function. Okay. And after that you are freeing the memory. The error will be uh, displayed. That's all. Okay. Is returned. Okay, so and here I have changed one more thing. What you can do is explain. What you will do is instead of giving like this, say exclamation NVCC file name, the output, and the what is the output you need. So that you can give in a single cell. After that again exclamation dot slash. So what is the output file name you can give. So instead of giving that, so you can give double percentage shell. Okay. So what happens is okay. So there is no error. So max error is given as 0. Okay. So here what I have written is NV profiler. Okay. So what about the threads have been executed? Okay. How many processes have been executed? Okay. So everything will be displayed here. Okay, for all the programs and all, so you can run the NVProf. Okay, the profiling we'll see in the after in the next class. Okay, but anyhow, I'll give some introduction. And there are 1134 processes are there. Our output is 0. And what is the GPU activities? How many API calls made? How much time is needed for executing this function, how much time it takes for executing the next one. So all the things have been there in that particular NV profiler. Okay, there are some profile visualizations are available. Okay, so it will provide some performance informations of the GPU. Okay, while executing some CUDA programs. You can use it. You use this NVPro for C or C++, whatever maybe it is. For all the programs, you can try. So execute, and after that, this is a statement. Okay, NVPROF. So these are all the things happened while executing this one. Okay, for these and all, the minimum times required, and so our device is Tesla T4. Already you know that. The runtime T4. total time required for host to device. Okay, and host to device data transfer, and device to host data transfer. So how long the GPU page fault proves, total CPU page fault. So all the things we can get it from there. So if you want to reduce the execution time, and from there, what are the functions you require, what are the functions you didn't require, you identify and you can remove all those things. Okay, please make a note of it. Say nvprof dot slash the output file name. Okay, that's all. So instead of giving exclamation, you can give this one. We'll see some other programs. So barrier, see here. Uh, Here one device variable is there. So then after that the ID is calculated and the threads have been synchronized. And if the binary value is this one, and we are printing, there is no global barrier, and just your and n size and block size is given. The n size has to be divided by block size comma block size. Okay, so already we have executed this one, and based on the number of threads, and so this will be printed so many times. Okay, and see here 1024 is divided by 64. We'll be getting something like 1024 divided by 64. You'll be getting 16. So there are 16 blocks. Here there are 16 blocks and the block size. So each block contains 64 threads. Okay. So it is there so many times. Okay. So and while using barrier, what you have to do is we have to use some variable volatile. Okay, and see here again same binary and counter is used. It as a volatile, so you can use this device variable within that kernel program, and sync thread is there. And what happened? So once the global barrier is over, okay, so what the value it will be, it is calculated, that will be printed there. Okay, we'll see. And up to one stage, there is no barrier. So after that, so it is simply calculating some array values and all. So we have given sync threads. Okay, if the value is this, there is no barrier. So after that, we are having another one kernel. Okay, so barrier in the sense all the processes are waiting until everything will be executing. Okay, so until this there is no barrier. Once after that you're having some barrier, that the synchronization is needed. Okay, see here the barrier starts here. The counter variable will be incremented with the help of atomic INC. Okay. See, if you are not using atomic INC and all, we can say there is no barrier or there is no synchronization. Okay, so even though we are using the sync threads, so uh, okay, it may have something like, but uh, all the threads have been wait until they were executed. Okay, so in the barrier, what happens is, so it won't allow to access. Okay, so it won't allow to access that memory location by different threads. Okay, so that has to be done with the help of atomic int. Okay, even though you have used the sync threads. So in global void K2 int, the K2 counter is assigned as 0. So after that, we are having another kernel for getting the ID value. So, so here it is having printing some values of ID. Okay. And after that, we are having the atomic INC and signed of K2 counter and plus 1. Okay, the n value is incremented here. Okay, so K2 counter is not equal to 1. Okay, not equal to n. We are stopping the barrier here. Okay, so it will shows. So what happens after the barrier? Okay, here again, simply the kernel is launched and the it is synchronized. So once the value is beyond this, so it will go to the barrier and executing the same thing. K2 int, see here K2 int, and K2 counter is 0, initialized. After that, K2 is called. K2 int is executed in 1 comma 1. Okay, simply single block, single thread is used and assigned value is 0. And K2, you are having actual what number of blocks and threads you needed, that is given. So, and K2 is called, here, where is here? Here it is K2 counter. Okay, so what happens is, so initially it is printed until this condition. Okay, so there is no global barrier. Barrier it says. After that it is initialized. So after that, after the next kernel is called. It is executed once. Okay, so we are not printing this. After that it is called. So while calling this, we are using atomic ANC. So uh, and the counter value is incremented from n plus 1. Okay. So what is the value of n? After that, so here the binary of n, that n has some value. Okay. So after that, what happens? That n value will be incremented. 767 up to 767, there is no global barrier. After that, it moves to initialize and move to the barrier location. Okay, so it's just simulating what happens while doing barrier and all. After that, the next statement is executed. So here you are getting some random values and all. Until this, so the ID value is incremented. See here, 640, 641, likewise it goes on up to this. After that, also we are having some ID values. Okay, randomly. Okay, so there is no synchronization. The last kernel. Oh, sorry, I didn't executed that program. It says the application is not found. Oh, sorry. Here the application name is B1. You have to give B1. Copying that. So you have to give the output file name correctly. See here all those things. Okay, K void. After that, it is used K CUDA launch kernel PCA bus ID. So with the help of PCA bus only the data is transferred. Then it is having CUDA device country, synchronize. It is getting attribute name, count, get log, loading mode, and okay. So these functions have been used. Here also you can try. It is B2. For all the programs, you can use the NV Prof. Give B2. They are yeah, it came. First you have to do this. Next you have to do this. Yeah, this program is having some error. So just leave it. It would, after that, we'll give. Okay. So 1315 threads it has used. Okay. So I didn't explain the threading and that means sorry, it's synchronization in detail. So I have given a little bit glance about what happens in data race and synchronization barrier. So everything I have given a small insight only. So there are a lot of things behind that. Okay, uh, we have to complete some more things in the next 2 or 3 classes. Okay, we are having 3 more sessions. So I'll give some glance about that. So, and that's all about today's session. Okay, if you have any doubt, you can ask me. Thank you. So we'll see you tomorrow.